valence shell electron pair repulsion theory, or Vsepr theory. Vsepr theory allows us to predict the geometries of molecules by looking at the regions of high electron density around the central atom. A region of high electron density can be a bond, or it can be a lone pair of electrons. The basic idea of Vsepr theory is that electrons want to be as far apart as possible, and this gives rise to 5 different electronic geometries, depending on the number of regions of high electron density around the central atom. When we distinguish between lone pairs and bonding pairs of electrons, a bonding pair is a pair of electrons that is shared between 2 atoms. A lone pair of electrons is associated with only 1 atom. Lone pairs take up more space than bonded pairs. To determine how many bonding and lone pairs we have, we're going to draw the Lewis structure. You can use this method described under letter G, but I will always use the Lewis structure. So I'm going to draw the Lewis structure for all of these. First type of molecule, AB2 type molecule. A stands for central atom, B stands for bonded atoms. So 1 central, 2 bonded. Example is BeCl2. You see from the Lewis structure that I've drawn, the bond angle is 180. It's a linear molecule. AB3 type, 1 central atom, 3 bonds. BF3 is an example. The bond angle between the bonds is 120 degrees. This is a trigonal planar geometry molecule. 3 regions of high electron density. AB2 type molecules. 1 central atom, 2 bonds, E stands for lone pairs. So this type of molecule has 1 lone pair. SNCl2, for example, you see the lone pair that I've circled. Lone pairs take up more space than bonded pairs, so the bond angle between the chlorine is 110 as opposed to 120 in the trigonal planar. Since we have a lone pair, we have to distinguish between electronic geometry and the molecular geometry. Electronic geometry refers to the distribution of electron pairs around the central atom. Electronic geometry is trigonal planar for SNCl2 because there are 3 regions of high electron density. Molecular geometry refers to the arrangement of atoms around the central atom. The molecular geometry of SNCl2 is bent. I want you to know the molecular geometries. Anytime you have a lone pair of electrons, the electronic and molecular geometries will be different. AB4 type molecules. SiH4 is an example. This is a tetrahedral molecule. All the bond angles are 109.5 degrees. This is a 3-dimensional molecule. It is not a flat molecule like the previous models. AB3 type molecule. 3 bonds, 1 lone pair. NH3, for example, the nitrogen has 1 lone pair. 3 bonds, 4 regions of high electron density. Because there is a lone pair, the electronic and molecular are different. But again, I want you to know the molecular geometries, which in this case is trigonal pyramidal. The bond angle is 107, which is less than the tetrahedral, because lone pairs take up more space than bonded pairs of electrons. AB2 type molecules, 2 bonds, 2 lone pairs, water, for example. Since there are lone pairs, electronic and molecular geometries are different. The molecular is bent, and the bond angle between the hydrogen and oxygens is 104.5. AB5 type molecules, 5 bonds, PF5, 5 regions of high electron density, electronic and molecular geometries, trigonal bipyramidal. This one has 2 bond angles, 90 and 120. AB4 type, 5 regions of high electron density, but because of the lone pair, the molecular is different than the electronic. Know the molecular, distorted tetrahedral, bond angle. There are 2 for this one, 90 and 110. And then AB6 type molecules, 6 regions of high electron density. Molecular and electronic geometries are octahedral. The bond angle is 90. When you have compounds containing multiple bonds, again, we're going to draw the Lewis structure. So for example, CO2 there's going to be 2 double bonds around the carbon. So double bonds will count as a single bond when we're predicting the geometry. This is a linear molecule. This is an AB2 type. There are no lone pairs around the carbon, so it's linear, and the bond angle is 180. So just like with all of the other compounds before, draw the Lewis structure. If you have polyatomic ions, one electron is subtracted for each positive charge and one electron is added for each negative charge. pH4 plus, for example, I'm subtracting a valence electron from phosphorus to give me 4 regions of high electron density. So the Lewis structure gives me a tetrahedral geometry and the bond angle is 109.5.